Now let's see what happens when airplane number 1 turns and goes back to try to get back with the same track as airplane number 2. We see that airplane number 2, let's take a look at what happens after 6 minutes. So in 6 minutes, airplane number 2 has traveled 10 kilometers. And at a 45-degree angle away in 6 minutes, airplane number 1 has traveled 10 kilometers. But notice that in the direction that airplane number 2 is traveling, airplane number 1 has only gone 7.07 kilometers. And of course, from the perspective of airplane number 1, airplane number 2 in that direction has only gone 7.07 kilometers. Now we're going to make a 90-degree turn, keeping that 45-degree angle to this track just for the easy math. And airplane number 1 is going to return back to airplane number 2, and airplane number 2 is going to keep traveling. And what's going to happen is, after another 6 minutes, airplane number 1 has traveled 10 kilometers, but only, well, let's look at the numbers here, 0.707, 0.707. So airplane number 1 has gone a total in the direction that airplane number 2 is traveling. Airplane number 1 has only made it 14.1 kilometers. And once again, the reason I like these 45-90 triangles is because I can remember that number. So airplane number 2 has traveled 20 kilometers in 12 minutes. But airplane number 1 has actually also traveled 20 kilometers, but in the direction that airplane number 2 is going, it has fallen behind by about 6 kilometers, a little under 6 kilometers, so that it meets at 14.1 kilometers. So by traveling out and back, airplane number 1 has lost ground to airplane number 2 and can never make it up as long as airplane number 2 does not change its course or speed. So let's do a quick recap to make sure we're following along here. The airplanes are traveling at the same speed. They always travel at a constant speed of 100 kilometers per hour. When they're traveling together, they're between the 2 layers of cloud, so they have no clues as to what direction or speed or anything they're going. Each observer feels like they are stationary and the other plane is stationary. But when one plane changes its direction, travels in another dimension, then it's going to fall behind in the dimension that the other plane is going, and the one that has changed direction will look at the other plane and see that it has fallen behind in the direction that it is going. So each observer sees the other airplane falling behind in the frame of reference that they are in. And then when the plane turns back, it will never be able to catch up because it made this deviation. So in this particular scenario, it has lost 29% of the distance that airplane number 2 has traveled. So by going at the same speed but in another direction, it has lost ground to the first one and can never catch up. So once airplane number 1 changes its frame of reference by going in a different direction, each observer sees the other airplane falling behind. And even when it turns, they end up still seeing each other falling behind. And I forgot something very important to say about this turning point. What happened to the perspective of the observer in airplane number 1? At this point, flying out here, that observer has to look over his right shoulder and behind to see airplane number 2 because it's falling behind. But when he turns, what happens? Now, here's airplane number 2 right here. And so airplane number 1 is now at about what? About maybe the 1 o'clock position. So from the viewpoint of the observer who went out and back, that observer is going to see, I'm looking behind here, the airplane go from behind. He's going to turn, and now the airplane's in front of him. Look at that again. So the observer in airplane number 1 who went out and back, as he's going out, he sees airplane number 2 over there. But as he turns, he now sees airplane number 2 ahead of him. So when he changes his frame of reference, he goes from a frame of reference where airplane 2 is behind him and turns, and now he's in a new frame of reference where airplane number 2 is ahead of him. But even though in this direction he's only traveling 70.7 kilometers per hour, airplane number 2 still ends up ahead of him. It takes him time to get back over here, and by the time he does, airplane number 2 has gotten way ahead and is about 30% ahead. Or in other words, airplane number 2 has traveled 1.41 times the distance of airplane number 1 in the direction that airplane number 2 is traveling. Sounds kind of complicated. Let's take one more quick look at it. When they're diverging apart, each observer sees the other one falling behind and has to look over his shoulder to see the other one. But when airplane number 1 turns around, he changes his perspective from where airplane 2 is behind to where airplane number 2 is in front. And he can never catch up as long as airplane number 2 never changes his course and speed. So hopefully that makes a lot of sense. That's something we could experiment with every day. We are simply working in 2 dimensions in a 3-dimensional space. Now I'm going to add a 4th dimension. That 4th dimension is time. And the problem is I only have a 2-dimensional whiteboard to explain this. So what I have to do is either combine all 3 dimensions of space into 1 dimension, or just confine myself to 2 dimensions. 1 dimension of space and 1 dimension of time. Either way works. However you can wrap your mind around it, use that. So let's put our 2 airplanes. They're sitting next to each other, not moving. Are they moving? Yes, they are. They're moving through time. So let's have a graph where time is that direction and space is to the left and to the right. So we have the 2 airplanes just sitting together. They are not moving in space, but both are moving at the same speed through time. Now, an interesting thing about the calculations, it turns out that we move through time at the speed of light. Interesting implications about that, but I'll talk about that another time. But just for the representation, we just need to look at some vectors, and that's what we're going to do. So the planes are now not moving in space, but they are moving in time. So here we go. There are the planes moving in time, and there's their frame of reference. As far as time is concerned, there's forward, there's backwards. Left and right are in space. Left in space, right in space. They're both the same. So now what we're going to do is put airplane number 1 on a dolly, and we're going to shove it away at 70.7% of the speed of light. Yes, we are fast. So away it goes at 70.7% of the speed of light. So it's going to be moving through space. Let's make it in that direction at 70.7% of the speed of light. What's that going to do to us? Because we just said, well, the speed of time is equal to the speed of light. So that means that plane, let's just move these down a little bit to make a little room. Here are the 2 planes. And airplane number 1 has moved off in that direction because it has gone at 70.7% of the speed of light. So in the frame of reference of airplane number 2, airplane number 1 has gone off in another dimension. So we already saw that if we have 2 objects traveling at the same speed through 1 dimension, if one of them turns and travels through another dimension, it is going to trade speed in the first dimension for speed in the second dimension. So we're going to have a trade-off, just like we did before, and basically we're going through space-time at a 45-degree angle. And what's going to happen? This is going at 70.7% of the speed of light in that direction, and it's going to go 70.7% of the speed of time, whatever that is, in that direction. So what's happening? The observer in airplane number 2 looks at airplane number 1 and sees it falling behind in time. When we had 2 spatial dimensions, when one plane turned and traveled in 1 dimension, he lost ground in space. Now that this dimension is time, when this plane turns and travels in that direction, he's going to lose in the dimension of time. So this airplane is going to fall behind in time. Likewise, he looks back over at airplane number 2, and he's going to see airplane number 2 falling behind in time. So either observer is going to see the other one falling behind in time. Simple Euclidean geometry meets the math of the Lorentz transformation and shows us visually that this time dilation, this slowing down of time, is something that we can visually wrap our minds around. Now, it's very important to understand one misconception about special relativity is that as you go faster, time slows down. No, it doesn't. The observer in airplane number 1 sees time going at the same speed, at, well, speed of light. So there goes time at the speed of light, but the observer in airplane number 2 looks over here and sees airplane number 1 falling behind in time, so he sees him going through time slower. And if he could somehow see the clock in airplane number 1 in real time, he would see it going slower. And the observer in airplane number 1 looks back at the airplane number 2 and sees exactly the same thing, because what's happened? We've rotated our frame of reference. So now that is time and space is that way. So his whole frame of reference is rotated. He's rotated time. This is why there are some physicists who are starting to think that maybe time has 2 dimensions rather than just one. I'm not going to go there, but this is what we see happening. Remember that time must be equivalent to the other 3 dimensions, and no observer can be special. Every observer has to see everything the same. So by going through space, he has changed his direction through time, and therefore time must be that way to him, space must be that way, so every observer sees everything exactly the same. So time is not slowed down for this observer, but he looks back at airplane number 2, and it looks to him like airplane number 2 is falling behind in time, and if he could see the clock in airplane number 2, he would see it ticking slower than his own clock. So see how adding that 4th dimension of time kind of makes what's understandable. Of course, it's not really changing its length, but in time, it has gone through less time. In this case, that one has gone through less time. So it becomes very real. And likewise, let's draw these airplanes with their 100-meter long fuselages and 100-meter long wings again. 100 meters each. And this one's gone over this way, 100 meters each. And look, in space here, 100 meters. Don't need that there. Over here. Now, in this airplane's space, the wingspan of this airplane has shortened to 70.7 meters. So, and that's all he can deal with. He has measuring equipment. He goes and measures, and he's going to see, you've gotten short. And here's another implication that isn't maybe as weird as you think, but the rear of the airplane has moved forward in time, and the front of the airplane has moved backward in time, so that the time taken up here is whatever it is, let's say 100 somethings. Over here it's 70.7 somethings. So not only is it length contracted because it's rotated in space-time, the rear has also come forward and the front has gone backward in time. And that's not quite as weird as you might think, and I'll show that in just a minute. But that's what we see when we add time as another dimension. So now the airplanes have diverged. They're still traveling the same speed through time, but this one has traded some of its speed through time, through speed, through space from this frame of reference. And so he has fallen behind in time. But his frame of reference, it looks like he's the one who's traded some speed for time and has fallen back in time.